FP1 numerical methods, example 1. We're going to start looking here at the first of the three methods, which is called interval bisection. The word bisect means to cut in two, and that applies here in this example as well. So this is the method, the steps that we need to look for. So locate an interval in which there is a sign change, i.e. where a root occurs. We take the midpoint of this interval that we've identified as our first guess, and then we use that to narrow down the process, cutting the interval in half subsequent times until we get to the sort of accuracy that we're looking for. So that will become clear when we do this first example. So we've got here a quartic equation. You probably won't know how to solve quartic equations, it's very complicated, and we don't actually cover them at A level. So it says, show that this equation fx equals 0 has a root in the interval 1.2 to 1.6. Now remember, we're looking for a sign change to show that there must have been a root. So I'm going to start by calculating f of 1.2 and f of 1.6. So I'll pause the video at this point and work out the values of those. So you should have got for f of 1.2 minus 2.5424. And if you sub in 1.6, you should have got 7.4416. You can see that this first one is less than 0 and the second one is greater than 0. So writing this shows the examiner that you're considering a change of sign. And then we need the magic words, which will get us the other marks, which is this. Sign change indicates a root in the interval, and then I'll use those round brackets, 1.2 to 1.6. Okay. So that's the first part done, showing that there is a root in that interval. And now we're going to look at the actual method that we're going to use to narrow down the calculations and see if we can get a little bit closer to that root. So it says use interval bisection 3 times. They very often tell you how many times to apply a method. Now what I tend to do is draw a bit of a line to represent the interval. So we know that the interval is 1.2 and 1.6, and we knew that 1.2 gave us a negative value, negative, and 1.6 was up here, it gave us a positive value. So somewhere in between, it must have crossed through the axis and we must have had a root. So the first thing we're going to do is choose the midpoint of this interval, because this method is called interval bisection. And the midpoint of 1.2 and 1.6 is 1.4. So we're going to look at 1.4 and we're going to work out whether the graph has already crossed through or whether it crosses through after that point. And the way we're going to do that is by looking at the sign, in other words, whether it's positive or negative. So same again, pause the video, work out f of 1.4. Now if you work that out, you should have got 1.4736. It's positive. It's greater than 0. So that means that we've already crossed through the axis by the time we've got to this point, and it's already above. So that means that the root must have occurred somewhere between 1.2 and 1.4. So what we sometimes do is cross out the bit that we're not interested in anymore and just focus on the first part. Same thing again, we look at the midpoint, 1.3. And if you substitute 1.3 into the equation, see what you get. I got minus 0.75-ish. It was negative anyway, we're more interested in the sign. So what that means is that the graph is still below the axis. If it was positive, it would have already crossed through, but it's still negative. So that means that we're still below the axis. So the crossover point must have been somewhere between 1.3 and 1.4. So we're not going to look at this first part anymore. And now we're interested in 1.3 to 1.4. So interval bisection one more time. The halfway point of 1.3 and 1.4 is 1.35. And so substitute that in again. And we get 0.302. It's positive. So what does that tell us? Well, it tells us that the root must occur in the interval where the sign change occurs. So we have a negative and a positive. Don't want that part anymore. So it's in the interval 1.3 to 1.35. So any estimate you came up with within this interval would be a better estimate than the one that we started with. And you could almost argue that the best guess, knowing that it's in this interval, would be the midpoint of that interval that we've just identified. And we could keep going and going and going, half in the interval every time, until we get a really, really good approximation.